Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 is, what is the ground state electron configuration of oxygen? Okay, so oxygen. And when we say ground state configuration, this just means that electrons in the oxygen atom weren't lost or gained. So when we want to find the electron configuration, we do a set of steps. So the first is to divide your periodic table into the different orbitals. So for example, the S block is this, the left two columns here. The P block is this whole green rectangle, and the D block are the middle transition metals, and the F block are the last two rows, which are the lactanides and actinides. So starting from hydrogen, we move left to right across the periodic table, writing the row number and then the block letter right after it until we get to our desired element. So in our case, this is oxygen. So oxygen is found right here, atomic number 8. So that means it contains 8 protons and 8 electrons in its ground state. So after we write down the electron configuration, we can double check that it's right if we count out the number of electrons that can be summed up in the superscripts of our electron configuration. So starting from hydrogen, I'm going to write the row number, which is 1, and then the block letter, which is S, and then a superscript of 2 to show that there are 2 electrons in this orbital. And this corresponds to the same as hydrogen and helium's electron configurations. So then moving down to the next row, we have 2s2, and then across to 2p, and then we count up to oxygen, so 1, 2, 3, 4. So the electron configuration of oxygen is 1s2, 2s2, 2p4. And we can double check by adding up all the superscripts to make sure that we have 8 electrons. So 4 plus 2 plus 2 is 8. So we know that this is the correct answer. Now let's see what the junior tutor said. 1s2, 2s2, 2p4. Explanation: an electron's electron configuration, or an element's electron configuration, is a numeric representation of its electron orbitals. Electron orbitals are regions around an atom's nucleus where electrons are likely to be located. An electron configuration can tell a reader how many electron orbitals an atom has, as well as the number of electrons in each of its orbitals. So it shows the distribution of electrons of an atom in a molecule. The area where the electrons orbit is called an electron shell. As an atom or molecule gains electrons, they fill different orbital sets according to a specific order. So each set of orbitals contains an even number of electrons when full. The sets of orbital are the S, which can hold 2 electrons, the P, which can hold 6, the D can hold 10, and the F can hold 14. So when writing electron configuration, you first find the electron's atomic number. Each atom has a specific number of electrons associated with it. Locate the element's chemical symbol on the periodic table. Number 2 is to determine the atom's charge. Uncharged atoms will have exactly the number of electrons as represented by the atomic number. 3 is to write the electron configuration notation. Electron configurations are written so as to clearly display the number of electrons in an atom as well as the number of electrons in each orbital. Each orbital should be written in sequence with the number of electrons in each orbital written in the superscript to the orbital name. The final electron configuration is a string of orbital names and superscripts. Step 4 is to fill in the orbitals according to the number of electrons in the atom. And then in writing the electron configuration, we fill in the electron orbitals starting with the lowest energy, following the Aufbau, Pauli exclusion, and Hund's rule. Ground state oxygen atom has 8 electrons. The first 2 will go into 1s, next 2 go into 2s, and the last 4 go into 2p. Yep, so this solution is correct. Okay, so question number 2. What is the correct name for the compound N2O4? Okay, so before we try to answer this question, let's try to figure out the type of compound we have. Since depending on the compound, they would have a different rule to name. So we have nitrogen and oxygen, which are 2 nonmetals. So this means we have a covalent compound. And since there's only 2 of them, we have a binary covalent compound. Okay, so since we know that we have a binary covalent compound, we can write out the rules on how to name these types of molecules. So first, we would write the first element. And you would use a prefix if you have more than one atom. So in our case, we have 2 nitrogens, so we would have to use a prefix of di. So let me quickly go over all of the prefixes on this side over here. 1 is mono, 2 is di, which is what we'll be using, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. So these are all the different prefixes. I'll just put it in a box so that we can take note of it. But the second step of naming binary covalent compounds is to then name your second element. And for your second element, you would always use a prefix. And you would change your ending to end in "ide." So sometimes you kind of have to tweak your element name in order to end it in "ide." So for example, with oxygen, it wouldn't end in like oxygen-ide, it ends in like oxide. So let's try to name our compound. We have 2 nitrogens, so we write di-nitrogen. And we have 4 oxygens, so we use the prefix of tetra. And in the case of oxygen, it starts with a vowel, so we would just use tetrox. And then the ending is "ide." So the name of that compound is dinitrogen tetroxide. Okay, so let's see what the junior tutor said. Naming compounds follow a systematic method. To name a binary covalent compound, the steps below may be followed. Step 1 is to check the first element. If the element has a subscript of 1, name the element as it is. For example, in CH4, C is just named as just carbon. If the element has a subscript of greater than 1, add a prefix before the name of the element. For example, in N2O5, N is named dinitrogen. 2. The second element will always have a prefix whether or not its subscript is greater or 1. Moreover, just like the naming of the anion in an ionic compound, we should take the base name of the element and append an "ide" to it. For example, in CO, oxygen is named as monoxide, while in CO2, oxygen is named as dioxide. 3. Put together the names in the previous steps. So, for example, CH4 is named carbon tetrahydride, and CO is named carbon monoxide. In N2O, the first element, nitrogen, must be named as dinitrogen, while the second element, oxygen, must be named as tetroxide. Therefore, the complete name of N2O4 is dinitrogen tetroxide. Yep. So this solution is correct. Okay, so question number 3 is to draw the Lewis structures of 2 isomers of C3H6. Okay. So usually when you're just given a formula and you need to write a structure, I always like to find out what the structure would look like if it was all just single bonds going across and then just adding the hydrogens. So this is the simplest hydrocarbon that you could get if you had 3 carbons and hydrogens. So now at this point I like to count to see how many I've drawn. So I have 3 carbons obviously, and then 1, 2, 3, 4, 5, 6, 7, 8. So we have more hydrogens than we need. So at this point, if I were to remove some of the hydrogens, so let's say I remove 2 of them, and if I were to add a double bond, I'll just put the ones that were erased. And now if I had a double bond in my structure and count out the hydrogens, 1, 2, 3, 4, 5, 6, I now have the correct structure for C3H6. So the question asks for 2 Lewis structures of this molecule. So notice if I switched places, if I put the double bond on carbons 2 and 3, it's still technically the same molecule since it would still just be at the end. So what we could also do is make a cyclic structure. And then just have all the hydrogens. So each carbon needs 4 bonds. So each of these carbons has an extra hydrogen. And now let's count out. We have 3 carbons and 6 hydrogens. So this is also a valid structural isomer of C3H6. So now let's try to name these. We have a 3 carbon chain. So we know that the parent is prop. And the fact that it has a single double bond means that it just ends in -ene. So this is propene. And in the case of our cyclic structure, when we have just a hydrocarbon like cyclic structure like this, we just need to add cyclo to the beginning and then just write propane. So the prop, because again we have a 3 carbon long cycle, and then ane, because there are no double bonds or triple bonds, they're all just single bonds. So these are the 2 isomers of C3H6, and if we look at the junior tutor's answer, you can see that they got the same thing. They also made sure to count out the number of valence electrons as well. So there are 3 carbon atoms, each with 4 valence electrons, and 6 hydrogen atoms, each with 1 valence electron, to have a total number of 18. So if we were to double check and count out how many electrons are participating in the bonds, so each bond has 2 electrons, then we can count out 9 bonds, so 18 in total. So none of the carbons or hydrogens would have a lone pair. So this solution is correct. Okay, so question number 4. What is the molecular weight of aluminum sulfate? So molecular weight, this can be the same thing as molar mass. So we need to find the molar mass of this compound. And in order to answer this question, we would need all the individual atomic masses of the elements involved in the compound. So for example, we have 2 aluminums. So we would do 2 times the molar mass of aluminum plus 3 times the molar mass of sulfur plus, and then here you can see that the oxygen has a subscript of 4 and the whole sulfate ion has a subscript of 3. So not only do we have to multiply the molar mass of oxygen by 4, we'd also need to multiply that by 3. So I'm just going to show multiple brackets so we can show how what that would look like. So 3 times 4 times the molar mass of oxygen. So now, again, we would just try to find these atomic masses on the periodic table. In the case of aluminum, its molar mass is 27 grams per mole. Sulfur is 32 grams per mole. And I've got to put all my brackets in for the oxygen, but the molar mass of oxygen is 16 grams per mole. Okay, so now we just add all these values up and we get a molar mass of 342.15 grams per mole. Okay, so now let's see what the junior tutor said. The molar mass of a chemical compound is defined as the mass of a sample of that compound divided by the amount of substance in that sample measured in moles. So they wrote out aluminum sulfate and then showed the equation and then subbed in all of the molar masses, added them up, and also got around 342. So this solution is correct. Okay, so question number 5. What is NH3? Is it a strong or weak base, a strong or weak nucleophile? Okay, so first let's draw out the Lewis structure for NH3. And to write out the Lewis structure, we need to calculate the total number of valence electrons. So for nitrogen, the nitrogen atom has 5 valence electrons, and in the case of a hydrogen atom, there is 1 valence electron, but we have 3 hydrogen atoms, so we multiply this by 3, and we get a total number of 8 valence electrons. So now I'll draw nitrogen as my central atom, and then 3 single bonded hydrogens. And now at this point, I like to count out how many electrons I've drawn so far. So in the case of these double bonds, each of them houses 2 bonding electrons. So far I've drawn 6, so I only need 2 more. So the last 2 I'll just put as a lone pair on my nitrogen. So now this is the Lewis structure of NH3. So now back to the initial question, is it a strong or weak base, a strong or weak nucleophile? So in the case of NH3, NH3 is actually a weak base. So this means it only partially dissociates into its ions. In solution. Is it a strong or weak nucleophile? So NH3 is actually a nucleophile. And this is due to nitrogen's lone pairs. So these lone pairs, they provide electrons to form covalent bonds with other atoms. So let's see what the junior tutor said. NH3 is a nucleophile because it has a lone pair of electrons and a partially negative charge on the nitrogen atom. A nucleophile is a reactant that provides a pair of electrons to form a new covalent bond, so nucleophiles are Lewis bases. NH3 is a weak base because it only partially ionizes and dissociates in water. NH3 has a stronger nucleophilic character than a water molecule. The oxygen in the water molecule isn't likely to bond with any carbon atom compared to the nitrogen atom because oxygen is more electronegative than nitrogen. It holds onto its lone pair tightly than nitrogen. Okay, so this solution is correct. Alright, so on to question number 6. What are the electron and molecular geometries respectively for the carbonate ion CO3 2-? So before we get into the geometries, electron and molecular geometries for this ion, we need to first draw out its Lewis structure. So we need to first determine the total valence electrons for this ion. So in the case of a carbon atom, carbon has 4 valence electrons, and oxygen atoms contain 6, and we have 3 oxygen atoms, so we multiply this by 3. And notice that the ion has an overall 2- charge, so I'm going to add an additional 2 electrons to our total number. And if we were to add this all up, we would get 24 valence electrons. Okay, so first I would draw out my carbon as my central atom, and then see what happens if I just have single bonded oxygens all around. And I'll draw out all of my lone pairs. And at this part, I like to count out how many electrons I've drawn so far. So in the case of all of the bonds, each bond contains 2 bonding electrons, so we have 6. And then each oxygen atom has 6 electrons. So we have 24 drawn so far, but if we look at our carbon atom, it doesn't have a full octet. So I need to make one of these oxygens double bonded and erase one of the lone pairs. And now if we count it out, I still have 24 electrons, except this time my carbon is has a full octet. So now I have my Lewis structure, and these 2 oxygens here have a negative charge. So we know that this is correct because that's what we're looking for. So I can also draw the resonance structures just by showing how each oxygen can have a double bond. Okay, so these are all the different resonance structures that you could have for this ion. Okay, so now we need to find out the electron and molecular geometries for this ion. So let's just look at one of the structures. And we're focused on our central atom, which is the carbon. So carbon has 0 lone pairs, and it also has 3 bonded atoms. So all those 3 oxygens. So at this point, we would use the Vesper table to help us try to find out the type of geometry this ion has. So this is a Vesper table, and it's really helpful because when you match up the type of molecular shape you have, it'll tell you the type of hybridization and the different bond angles that you would find in your molecule. So in our case, we have 3 bonded atoms and 0 lone pairs. So this means our molecular shape and our electron geometry, they're both trigonal planar. And the carbon is sp2 hybridized. And the bond angles are 120 degrees. Okay, so let's see what the junior tutor said. From the Lewis structure of the carbonate ion, it can be seen that the central carbon atom does not have any lone pairs. For any molecule where the central atom does not have any lone pairs, the electron geometry will be the same as the molecular geometry. So then they drew out all the Lewis structures. Using the AXE method of determining molecular geometries, for the carbonate ion, this is AX3, which it corresponds to a trigonal planar molecular geometry. Therefore, the electron and molecular geometry for the carbonate ion is trigonal planar. So this solution is correct. Okay, so question number 7. Draw a Lewis structure and any resonance form of benzene. So benzene is C6H6. So when we write out the Lewis structures, let's first find out the total valence electrons for benzene. So carbon has 4 valence electrons, and there are 6 carbon atoms. So we have 24. And for hydrogen, hydrogen has 1 valence electron. We also have 6. And this gives us 6. So if we add them up, we have a total of 30 valence electrons. So benzene is a cyclic hydrocarbon that contains the 6 carbons. So these are all the carbons in the ring. And in between every other carbon is a double bond. So this means that benzene is aromatic, and it's a very popular molecule because of its aromaticity. So this is one of the Lewis structures of benzene, and I can also show how the double bonds can kind of move around in the molecule to get a second resonance structure. So we get this. Okay, so these are the two resonance structures of benzene. And the junior tutor said benzene has a formula C6H6. Number of valence electrons is 30. Benzene is a 6-membered ring with conjugated double bonds. And then they drew out the two Lewis structures for benzene. So this solution is correct. Okay, so question number 8. Calculate the molar mass of salicylic acid, which is used to make aspirin. Fun fact. So salicylic acid has the formula C7H6O3. So to find out the total mass of salicylic acid, we would need all the different atomic masses of the different atoms involved in the molecule. So all of the atomic masses of these atoms can be found on the periodic table. And to find the total molar mass, it's going to be 7 times the molar mass of carbon plus 6 times the molar mass of hydrogen plus 3 times the molar mass of oxygen. So in the case of carbon, if we were to look up its atomic mass, it is 12.01 grams per mole. In the case of hydrogen, it's 1.01 grams per mole. And in the case of oxygen, it is 16 grams per mole. So now if we added up all these values, we get a total molar mass of 138 grams per mole for salicylic acid. Okay, so now let's see what the junior tutor said. In chemistry, the molar mass of a chemical compound is defined as the mass of a sample of that compound divided by the amount of substance in that sample measured in moles. Okay, so then they showed out how one would calculate the molar mass and also got 138 grams per mole. So this solution is correct. Okay, so question number 9. How many valence electrons does iodine, chlorine, and bromine have? So let's look at the periodic table. Let's just go to a normal periodic table. So fluorine, bromine, chlorine, and iodine, they're all found in period 17. So in period 17, they all contain 7 valence electrons. Okay, so I can draw out an example of like fluorine versus chlorine. So when we have a fluorine atom, if we find it on the periodic table, it has an atomic number of 9. So maybe this one's a little bigger. Not really. Anyways, yeah, the atomic number tells us how many protons are in the atom, and if we had a neutral fluorine atom, then we would have the same number of electrons as we do protons. So therefore, we have 9 electrons in a neutral fluorine atom. So in the first shell, we have 2 electrons. And the second shell can hold up to 8. But fluorine only has 9 electrons, so I just need to draw 7 more. 1, 2, 3, 4, 5, 6, 7. Okay, so valence electrons are the electrons in the outermost ring. And you can count out here that fluorine has 7 valence electrons. So now let's compare this with a chlorine atom. There are also 2 electrons in the inner orbital. But if we look at the atomic number of chlorine, it is 17. So that means a neutral chlorine atom has 17 electrons. So this second ring has the full 8. And now when we draw out our third shell, we've drawn 10 electrons so far, so chlorine has 17. So we just need 7 more. And again, you can see how chlorine also has 7 valence electrons when we compare it to fluorine, but its atomic diameter, the radius is much more bigger than that of fluorine. So the more we go down the periodic table, the bigger this radius gets. So let's see what the junior tutor said. There are 7 periods and 18 groups in a periodic table. The ground state's electronic configuration is the arrangement of electrons in the shell of an atom according to the increasing order of energy. Elements that belong to the same group in the periodic table possesses the same number of valence electrons. Iodine, chlorine, and bromine all belong to the same group, which is group 17 at the periodic table. So all these elements possess the same number of valence electrons. According to this, iodine, chlorine, and bromine have 7 valence electrons. I think I messed up the wording here. So period refers to the rows, but the columns are called just groups. So this is just called group 17. So I kind of caught that last minute while I was reading the solution. Group 17, 7 valence electrons. So this solution is correct. Okay, so question number 10. Draw all aldehydes and ketones with the formula C5H10O. Okay, so at first let's draw out all the different aldehydes we could get with this formula. So an aldehyde is when the carbon has a double bonded oxygen and this is at the end. Oops. Double bonded oxygen. at the end of the chain. But I'm just going to say at the end. So first, let's draw out our 5 carbons. So 1, 2, 3, 4, 5. So when you draw just the line structure of a compound, each of these different points corresponds to a carbon atom, and it's already assumed that all the hydrogens are there as well, so each of these have invisible hydrogens attached to it, but for clarity we don't include those. So these are all 1, 2, 3, 4, 5 carbons and all the hydrogens attached. So an aldehyde, again, is this double bond, and we know it's at the end because on the other side of the aldehyde there's a hydrogen. So this is an example of the simplest aldehyde you could have with the formula C5H10O. So now we just kind of experiment with all the different types of structures that you could get. So let's say we had a 4-carbon chain with the aldehyde at the end and a methyl group right here. This is also C5H10O. Now let's experiment again. If we had that same 4-carbon chain, we can draw the methyl group on this carbon now instead. And then I think our last option for an aldehyde would be a 3-carbon long chain. And our aldehyde right here. And this had 2 methyl groups attached to it. So this is another example that you could have. So I think those are all the different options we could have for an aldehyde. Now let's do the same thing for the ketones with the same formula. So ketones are similar to aldehyde in which they contain a double bonded oxygen, except ketones are found in the middle. So again, let's draw our most simplest 5-carbon chain. 1, 2, 3, 4, 5. And then a ketone would be in the middle right here. We can try another 5-carbon chain, and the ketone can be smack dab in the middle, like right here on carbon 3. Or we could have a 4-carbon chain and have the ketone right there. Okay, so these are the 3 different ketones that you could have with the formula C5H10. So now let's see what the junior tutor said. Aldehyde is a class of organic compounds in which a carbon atom shares a double bond with an oxygen atom, a single bond with a hydrogen atom, and a single bond with another atom or group of atoms, designated as R in general chemical formulas and structure diagrams. The functional group of an aldehyde is a carbonyl group bonded to a hydrogen atom and a carbon atom. Aldehydes with the formula C5H10 are given as below. Was given as above. So here they have the simplest aldehyde 5-carbon chain. Now this is a 4-carbon chain with a methyl group, a 3-carbon chain with 2 methyl groups, and then another 4-carbon chain, but the methyl group is closer to the aldehyde. So those are the 4 different structures For all the ketones, the functional group of a ketone is a carbonyl group bonded to 2 carbon atoms. So it's in the middle. Ketones with the formula C5H10 are the following. So this is the one that's right in the middle. This is one where you could have a 4-membered carbon chain. Oh, I forgot to draw. With an additional methyl group so that you could have 5 carbons. And then lastly, you could also just have a ketone on the 2nd carbon of the chain. So this solution is correct. Okay, so question number 11. What is the electron configuration for the ion Fe2+? So this is iron 2+. So first let's find out the electron configuration of iron. So when we write the electron configuration, we want to divide our periodic table into the different blocks. So the S block are the first 2 columns in blue, the P block is in green, the D block is orange, and the F block are these 2 rows, the lactanides and the actinides. So we find iron on the periodic table. You can see that it's right here, atomic number 26. And then starting from hydrogen, we go left to right and then down until we get to our desired element. So in the case of iron, we would go down and see 1s2, 2s2, and then here 3p6, or sorry, 2p6. Looks bad. 2p6, and then down to the next row, 3s2, and then across 3p6, and then once we get to the transition metal part, I like to write my D block in first, since they have a lower energy than our 4s orbital. So instead of doing 4s2 first, I'm just going to count up to my iron, which is 1, 2, 3, 4, 5, 6. So 3d6, and then I'm going to add my 4s2. So if we wanted to draw the shorthand configuration, we would find the noble gas that comes before iron. So in this case, it's argon. We'd put that in square brackets and then continue on with the rest of the electron configuration, which is 3d6, 4s2. Okay, so this is the electron configuration of a neutral iron atom. If iron were to have a 2+ charge, this means that electrons were removed. So specifically 2 electrons were removed. So if each of these superscripts corresponds to an electron, we just need to remove the last 2 electrons. So in the case of argon, in the case of Fe2+, it would be argon 3d6 if these 2 electrons were removed. So now let's see what the junior tutor said. An element's electron configuration is a numeric representation of its electron orbitals. Okay, so they go on and give their detailed explanation. And you need to follow the Aufbau principle, the Pauli exclusion principle, and the Hund's rule. They found the atomic number of iron is 26. Iron atom has 26, but iron 2 plus has 24. And they also got argon 3d6. So this solution is correct. Okay, so question 12. What is the Lewis structure of H2SE? So first we need to find out the total number of valence electrons in this molecule. So in the case of selenium, there are 6 valence electrons. And in the case of hydrogen, hydrogen has 1 valence electron, and there are 2 hydrogen atoms. So we multiply this by 2, which gives us a total of 8 valence electrons. So we draw selenium as our central atom, and then 2 single bonded hydrogens. And if we remember that each bond contains 2 bonding electrons, then I've only drawn 4 electrons so far out of the 8. So the remaining 4 I'm going to put as lone pairs on the central atom. And now we have 8 electrons, and both elements have a full octet, or in the case of hydrogen, it's just satisfied. And now let's see what the junior tutor said. Calculate the total valence electrons in the given molecular ion. Hydrogen belongs to group 1, so it has 1 valence electron. Selenium belongs to group 16, so it has 6. So they got 8. Connect all the atoms with single covalent bonds. And they counted out how many electrons they needed left. Place the remaining 4 electrons on the atoms so that the octet gets filled. So they put it on the selenium. And they also took the time to calculate the formal charge. So the formula for formal charge is number of valence electrons minus number of bonding electrons divided by 2 minus number of lone pair electrons. So both selenium and hydrogen have a 0 formal charge. And they got the correct answer. So this solution is correct. And I think we have time for one more quick question. What is the Lewis structure of IF2 minus? So to find the Lewis structure of this atom, let's find the total valence electrons. So iodine has 7 valence electrons, and fluorine also has 7, but there are 2 fluorine atoms, so we multiply that by 2. And the overall charge of the ion is -1, so we're going to add an extra electron. Oops. And if we add these all up, you get 22 valence electrons. So first I'm going to draw my iodine as my central atom. And then I'm going to draw single bonds to my 2 terminal atoms and add all of fluorine's lone pairs. So at this point, I count out to see how many I've drawn so far. So each bond contains 2 bonding electrons. So there are 2 bonds, so that's 4. And then each fluorine contains the 6 electrons in the lone pairs. So 12 plus 4. So there's only 16 that I've drawn. So I need to draw 6 more to get 22. So for the remaining 6, I'll draw them on my iodine. So now let's try to find out where that negative charge will go. So we can do that by calculating formal charge, which is the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. So let's do fluorine first. So fluorine has 7 valence electrons. The number of non-bonding electrons are the electrons in the lone pair, so 1, 2, 3, 4, 5, 6. Number of bonding electrons is 2 because there's one bond. So 7 minus 6 minus 1 is equal to 0. So now let's do the same thing for our iodine. Iodine has 7 valence electrons. The number of non-bonding electrons is 1, 2, 3, 4, 5, 6. And this time the number of bonding electrons, so since there are 2 bonds, there are 4 bonding electrons in total, divided by 2. So 7 minus 6 minus 2 is negative 1. So therefore the negative charge is shown on the iodine. So let's see what the junior tutor said. They got the same answer. So this solution is correct. Okay, so if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed the video, go ahead and give it a thumbs up and a comment. And yeah, so you can also share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.